Right now, in the Chilean desert, the largest camera ever built is beginning a decade-long experiment that's never been attempted before. Not just photographing space, filming it. 20 billion galaxies. 10 years. One continuous movie. Every 3 days, it scans half the visible sky. Every object tracked. Every change recorded. Stars exploding. Asteroids drifting. Black holes feeding. All in motion. But here's the problem nobody's talking about. This telescope will generate more data in its first year than every other observatory in history combined. 500 petabytes over 10 years. 20 terabytes every single night. And we don't actually know how to analyze it all. The Vera Rubin Observatory isn't just the most powerful survey telescope ever built. It might be the first scientific instrument that creates more discoveries than humans can process. This is the story of the 10-year movie, and why the scariest part isn't what we'll find. It's what we might miss. Every telescope is a time machine. Light takes time to travel. When you look at a star 10 light-years away, you're seeing it as it was 10 years ago. Look at a galaxy a billion light-years away, and you're looking a billion years into the past. But the Vera Rubin Observatory does something different. It doesn't just look back in time. It watches time move. Traditional deep-field astronomy, telescopes like Hubble or James Webb, work by staring at tiny patches of sky for hours, days, sometimes weeks. They go incredibly deep, capturing the faintest, most distant objects in exquisite detail. One image. One moment. Frozen. Survey astronomy is different. It's about coverage, not depth. It's about photographing huge areas of sky quickly, then coming back and doing it again. And again. And again. That repetition is the key. Because the universe isn't static. Stars explode. Asteroids move. Black holes flare as they devour matter. Distant galaxies brighten as their cores ignite, then fade as the fuel runs out. If you only photograph the sky once, you miss all of that. But if you photograph the same patch of sky every few days for 10 years, you create a movie. The Rubin Observatory will scan the entire southern sky, half the visible universe from Earth, every 3 days. Let that sink in. Every 72 hours, it captures 20 billion galaxies. 20 trillion stars. Millions of asteroids. Over and over and over. By the end of its 10-year legacy survey of space and time, LSST, it will have created roughly 3,650 observations of the same patch of sky. Astronomers call this time domain astronomy. The study of how the universe changes. And it requires something extraordinary. This is the LSST camera. The largest digital camera ever constructed. 3 meters long. Nearly 3 tons. 189 individual sensors working in perfect coordination. 3.2 billion pixels per image. To put that in perspective, if you wanted to display one full-resolution image from this camera, you'd need 378 ultra-high-definition 4K televisions arranged in a grid. One photograph from this camera contains more pixels than your eyes will see in an entire day of looking at screens. And it takes one of these photographs every 30 seconds. All night. Every clear night. For 10 years. The data problem is staggering. The observatory generates roughly 20 terabytes per night. That's about 4,000 full-length HD movies. Every single night. Over 10 years, that adds up to 500 petabytes, 500 million gigabytes. For comparison, the entire Library of Congress, every book, manuscript, recording, and photograph, is about 20 terabytes. Rubin will generate that much data before breakfast. The observatory is in Chile. The data center is in California. A dedicated 100 gigabit fiber optic line was laid across the Pacific just to handle the flow. But storage is only half the problem. The real challenge? Figuring out what any of it means. The Rubin Observatory wasn't built for one purpose. It was built for four, and each one requires time domain data. Mission 1, Hunt the Invisible. Dark matter makes up 85% of the matter in the universe. We've never seen it directly, but we see its effects: galaxies rotating too fast, galaxy clusters bending light from behind them. Rubin's time-lapse will track how galaxies move over the decade, how gravitational lensing changes as mass shifts, and how clusters evolve. This technique, weak gravitational lensing, measures how dark matter bends the light of distant galaxies. But you need lots of galaxies, measured repeatedly, to detect the subtle distortions. Rubin will measure 20 billion of them. Dark energy is even stranger. It's accelerating the universe's expansion, but we don't know why. Rubin will track distant supernovae, exploding stars that serve as standard candles for measuring cosmic distances, over time, refining our understanding of how fast the universe is expanding and whether that rate is changing. Mission 2, Guard the Planet. Right now, we know the location of about 1.3 million asteroids. Rubin will find millions more in its first 2 years. In just 10 hours of test observations in 2025, Rubin identified 2,104 brand new asteroids, including 7 near-Earth objects that had never been catalogued. For comparison, all other ground and space-based observatories combined discover about 20,000 new asteroids per year. Rubin alone will likely discover more asteroids per week than humanity found in the entire 20th century. And because it scans the sky every 3 days, it won't just find asteroids, it will track them, refining their orbits with every pass. This is critical for planetary defense. If an asteroid is headed our way, we need years, maybe decades, of warning to do anything about it. Rubin gives us that warning. But there's another asteroid mystery Rubin might solve. In 2017, astronomers spotted Oumuamua, the first confirmed interstellar object passing through our solar system. In 2019, a second one arrived, 2I/Borisov, an interstellar comet. 2 visitors in 2 years. Astronomers estimate that interstellar objects pass through the inner solar system roughly once per year. We've just never had telescopes fast and wide enough to catch them. Rubin will catch them. Estimates suggest Rubin could detect 1 interstellar visitor per month once the survey is fully operational. Imagine that, instead of 2 known interstellar objects, we could have hundreds by 2035. Mission 3, Catch the Transients. The universe is full of things that flash, flare, explode, and fade. Supernovae. Gamma-ray bursts. Tidal disruption events where black holes shred stars. Flare stars. Pulsating variables. Gravitational wave sources producing optical counterparts. These events are called transients, and they're everywhere, but only if you're watching when they happen. Here's where Rubin's time domain strategy becomes critical. Every image Rubin takes is automatically compared to previous images of the same region. If something changes, a new point of light, a star that brightened, a galaxy that flared, the system flags it within 60 seconds. 60 seconds from photons hitting the detector to an alert sent to astronomers worldwide. Those alerts trigger follow-up observations from other telescopes, spectroscopy to identify what the object is, multi-wavelength imaging to understand its physics. Rubin won't just find transients. It will catch them early, when they're still evolving, still telling the story of what happened. This is how we'll study the first moments after a supernova explodes. The first hours after a star gets shredded by a black hole. The fading afterglow of neutron-star collisions. Mission 4, Map the Milky Way. Our own galaxy is enormous, 100,000 light-years across, containing 200 to 400 billion stars. But we don't actually know its shape, structure, or full extent very well. Why? Because we're inside it. Imagine trying to map a forest while standing in the middle of it, surrounded by trees. Rubin will find a special type of star that helps solve this, RR Lyrae variables. These are old, pulsating stars that brighten and dim on regular cycles, like cosmic lighthouses. And because their brightness is predictable, astronomers can use them to measure distance. Find an RR Lyrae star, measure how bright it appears, compare that to how bright it should be, and you know how far away it is. In its first 10 hours of test observations, Rubin found 46 RR Lyrae stars. Over the full 10-year survey, it's expected to find 100,000 or more, some over 1 million light-years from Earth, deep in the Milky Way's outer halo. That data will let astronomers map the three-dimensional structure of our galaxy in unprecedented detail. For missions. Billions of objects. Trillions of measurements. And every single one depends on one thing, seeing the sky change over time. Let's talk about the problem nobody wants to admit. Rubin will generate 500 petabytes of data over 10 years. That's not just a big number. It's an unmanageable number. Every night, Rubin will detect roughly 10 million changes in the sky. Most of them will be false alarms, cosmic rays hitting the detector, asteroids we've already catalogued, known variable stars doing what they always do. But buried in that noise will be real discoveries. Supernovae. Interstellar objects. Near-Earth asteroids. Gravitational lensing events. Objects we don't even have names for yet. How do you find them? A human astronomer can carefully review maybe 100 to 200 candidates per hour. Let's be generous and say 500. That means it would take 20,000 hours, over 2 years of non-stop work, to review one night's worth of flagged objects. And Rubin operates every night. This is the data crisis at the heart of modern astronomy. We've built instruments so powerful that they generate discoveries faster than we can process them. The only solution is automation. Rubin's data pipeline relies on machine learning algorithms trained to recognize different types of transients, to filter out instrumental artifacts, to prioritize the most interesting candidates for human review. These algorithms have been trained on millions of synthetic events, simulated supernovae, asteroid tracks, variable stars, so they can recognize the real thing when it appears. But here's the terrifying part. Even a 95% accurate algorithm makes mistakes. If you're flagging 10 million objects per night, and your algorithm is 95% accurate, that's still 500,000 errors per night. Some of those errors will be false positives, flagging things that aren't real. But some will be false negatives, missing things that are. What if the most important discovery of the decade, Planet 9, an interstellar probe, a nearby supernova precursor, gets filtered out as noise? What if the algorithm isn't trained to recognize it because we've never seen anything like it before? This is the nightmare scenario. Not that Rubin won't make discoveries, but that it will make discoveries we never notice. That's why Rubin's data is public. Every image, Every measurement. Every flagged object. All of it goes into a publicly accessible archive. The hope is that thousands, maybe millions, of people will comb through the data, looking for things the algorithms missed. Projects like Galaxy Zoo have already proven this works. In 2007, researchers needed to classify the shapes of 1 million galaxies. They couldn't do it alone, so they put the images online and asked volunteers to help. Within a year, over 100,000 people had participated, classifying all 1 million galaxies, and discovering entirely new types of objects the professionals had overlooked. Rubin will need that same kind of crowdsourced effort, but on a scale 10,000 times larger. In June 2025, Rubin released its first public images. And even though the survey hasn't officially started, they're already breathtaking. This is the Cosmic Treasure Chest, a 25-square-degree mosaic of the Virgo cluster, about 55 million light-years away. It's made from 1,185 exposures taken over 7 nights. It contains 10 million galaxies. And that represents just 0.05% of the 20 billion galaxies Rubin will observe over the next decade. Look at this area, nicknamed Cosmic Drama. Bright foreground stars from our own Milky Way. Dozens of nearby galaxies, sharp and clear. And behind them, a sea of faint, reddish galaxies, some of the most distant objects in the image. Each one of those tiny red smudges is a galaxy containing hundreds of billions of stars. And this is just one image. Here's another early image, a mosaic of the Lagoon Nebula and surrounding region, made from 678 individual exposures over 7 hours. This is Hubble's view of the Lagoon Nebula, incredibly detailed, zoomed in on a region about 4 light-years across. Now here's Rubin's view. The Lagoon Nebula is 55 light-years across. Hubble captured a small piece. Rubin captured the whole thing, plus the Trifid Nebula, 2 star clusters, and a globular cluster containing tens of thousands of stars. Rubin's field of view is 4,000 times larger than Hubble's in a single shot. That's not better or worse. It's different. Hubble is a microscope. Rubin is a wide-angle lens. And that wide angle is exactly what time-domain astronomy needs. Because to track how things move and change, you need to see the whole sky, repeatedly. In just 10 hours of test observations, Rubin found 2,104 new asteroids, 46 pulsating RR Lyrae stars, and millions of galaxies. The real survey hasn't even started yet. Final testing wraps up in late 2025. The full 10-year survey begins in early 2026. Here's what's coming. Year 1, Rubin will collect more optical data than every previous observatory in history, combined. Year 2, the asteroid catalog will grow from 1.3 million known objects to potentially 5 to 10 million. Year 5, the time baseline will be long enough to detect orbital changes in binary stars, measure proper motion of distant galaxies, and track the slow drift of Planet 9, if it exists. Year 10, 500 petabytes. 20 billion galaxies. Trillions of measurements. The most complete movie of the universe ever created. And then the real work begins. Because the survey ending in 2035 doesn't mean the discoveries stop. Astronomers will be mining this dataset for decades. Students not yet born will write PhD theses on objects Rubin photographed before they were in school. If you want to explore Rubin's images yourself, visit skyviewer.app. You can zoom into these mosaics, hunt for faint galaxies, spot asteroids in the raw frames. It's extraordinary. The Vera Rubin Observatory isn't just a telescope. It's a time machine that watches time move. A cosmic surveillance system tracking 20 billion galaxies. A planetary defense network scanning for threats we haven't found yet. And a data challenge so massive, we're not entirely sure we're ready for it. But that's the point. The best discoveries are the ones you weren't prepared for. The ones that change the question. And somewhere in those 500 petabytes, in those trillions of measurements, in that 10-year movie of the universe, is something we've never seen before. The camera is rolling. The movie has started. Now we just have to watch.